we can see this that from E. coli we can also have a complex interactions here. So actually, what is the protein-protein interactions? This is a physical contact with high specificity formed between two or more protein molecules as a result of biochemical process influenced by interaction caused by electrostatic forces, hydrogen bonds, and hydrophobic effects. So this is the maybe more chemical or chemistry definitions. And honestly, I do not understand. If you ask me what about the electrostatic forces, hydrogen bonds, and so on. So I will make it simple that all interaction will be represented into graph. Node as a protein, node is a protein, and length of it is interaction. So if I draw, if I draw this is node and this is link. This is the, for example, protein 1, protein 2. So node is protein, and this is interaction. If you ask me what kind of interaction, so I cannot answer. Maybe this interaction is about the electrostatic force, hydrogen bonds, or something. Okay, this is I just define the scope of my talk. So this already I explained before. Protein-protein interaction is represented into graph. Protein as node and interaction as link or its. So why we use graph? Because graphs are everywhere. For example, if you use media social like Facebook or Twitter, then you can draw the why how the news, for example, spreads from one person to another person. So, for example, if you got information about something that you can track the information in Twitter from the network, the complex network like this, for example. Okay. Also, we also can find the network in co-expression network. Also in chemical compound. Also in social network like Facebook, Twitter, and so on. Also in pathway, for example, or program flow or protein structure. So graph as a mathematical notation is very, very powerful to draw the interactions between object with another objects. So this is the mathematical definition. A graph G defined as G is graph, VV is vertex or node, and it's or link. So this is a vertex V. This is E. I forget. I'm Indonesian, so I forget. V is vertices as node, E as its as link. So if we mention VG, so actually this is no empty set of vertices or nodes. Is I write EG, so a set of its pair of vertices. So it should be connected to minimum to should be connected to nodes. Yeah, sorry, link or it should be connected to nodes. And graph, maybe there in graph there is a direct graph. For example, if you go to the street around the kebun botanical garden in Bogor, there is a street that only one direction. So in this case, if we would like to describe to represent the street with the graph, so the graph is like this. You cannot, if there is a direction here, you cannot, so the direction otherwise is no meaning. So there is no meaning. Direction, for example, this is P1 and P2. If this is the graph, directed graph, so we cannot, there is no meaning the link between P2 to P1. Use the meaning is already started from P2 to P1. Sorry, P1 to P2. But if the drug is undirected, for example, like a protein-protein interaction here, so we just draw the graph like this. And we also have a terminology, we call it as adjacent nodes, that represented by using adjacency matrix. For example, if we have here node 1, node 3, node 2, node 5, node 1, node 2, node 3, node 5. So node 1, with node 1, we set 0 because there is no interaction between 1 and 1. Okay, because we just talk about the interaction between two nodes. So because 1 have a link to 2, so we set 1 value here for N1 and N2 for node 1 and node 2. But because there is no interaction between 1 and 4, so the set, then the value here is 0. This is the adjacency matrix. Where we use this because a computer only can proceed number or symbol that can be processed in computer. For example, the integer value like 1, 0 or numerics value can be processed in computer science. But if you give the information originally like this, computer cannot output something, cannot give the output for you. And also we have a path terminology, path and distance. Path is, for example, if you go from 1 node to 6 node, this is path. Also 1 from 2, 1 from 5, 1 from 1 to, sorry, from 1 to 2, 1 to 5, 1 to 7. This is path. So we have many paths here. 1, 2, 1, 3, 1, 4, yes, and so on. And length of path is, for example, if you go to 1 to 3, the length of path is only 1 because there is only one link here. But if you go to 3, there is 2, 1, 2. 2 go to 4, 4 also 2. But if you go to the path of 1 to 6 is 3 because 1. This is the path 1 to 2, but you also have the path of 1, 2, 3. This is the length of path is 1. This is length path of 2 and 1, 2, 4. And for example, 1, 2, 5, 6. Like this. But what is shortest path? For example, you can go to 6 from 1 to 3 to 4 to 6. This is the 4 length. But you can also 1 to then 5, then 7, then 4, then 6. this path is 1, 2, 3, 4, 5. 5. Oh, sorry, this is 3. 3. So this path actually is the same. The origin node is 1 and the objective node is the end node is 6. But this is the shortest path. This is the shorter path than this path, because in the first path we only have 3 links here to go from 1 to 6, but in the second path we should through the 5 length, 5 link, sorry, 5 link, 1, 2, 3, 4, 5. So this is the shortest path in this graph. Okay, the definition of shortest path is like that. So many path you can go, for example, from Tokyo to maybe, I don't know, to Osaka maybe, but you can get the shortest path, which path or which routes that are actually the shortest to go from Tokyo to Osaka, for example, like this. And also we introduce the bipartite graph, for example, here. Bipartite graph, actually the connection only exists from component of the one entity to another entity, and there is no connection between object or component inside the entity. For example, entity is compound, this is compound, this is protein. So we draw the interaction between compound and protein, but we cannot draw the interaction between a compound and compound, or protein and protein. This is, we call it as bipartite graph. Well, I mean, drug target interaction is example of bipartite graph. If we extend the interaction between compound, protein, and plant, like drawn by, like explained by Dr. Sony, then we can call it as a k-partite graph, where is k is related to the number of entity. For example, if plant, compound, and protein, so we can call it as 3-partite graph. If we have a relation between plant, compound, protein, and disease, so we have a 4-partite graph, like this. And we, in a graph, we also have a topology here. Topology is the way in which the nodes and its or links are arranged within a network. For example, degree of network is the number of that connect to a node. For example, this node 5 have 5 degree. Yes, 1, 2, 3, 4, 5. But node 3 only 3 degree. 1, 2, 3. But node here only have 1 degree. So intuitively, that node with high degree actually become a center of this network. Okay. And then centralities are the centralities, like between the centrality of that and then and etc. This describes how important the node or is for the connectivity information flow of the network. And the third terms is shortest path. I already mentioned or explained before, used to model how information flow. So usually we prefer to choose the path that very short and that shorter than others path, yeah, because it's more economically or more efficient or something. And high degree or nodes or hubs that provide a connectivity to the network. This is scale-free network. So scale-free network, like protein-protein interaction, is belong to the scale-free network. Is high degree nodes that provide high connectivity to the network, because in protein-protein interactions model, we find some protein that have a high degree. For example, in diabetes, insulin genes or protein have a high degree. So in the final project, this is actually something that should be noticed or should be highlighted, which actually the protein that have a highest degree in the network. In the final project, you will divide it into 7 groups. Yes, each group will have a different data. We have already, my institution already collected data from hypertension disease, Parkinson disease, Alzheimer's disease, arthritis disease, then coronary heart disease, and osteoporosis disease, and so on. Maybe tomorrow I will share the data in OCW. And also transitivity, the presence of tightly and connected nodes in the network clusters. So the question is how to find target proteins, or protein targets, or we can change the statement with has the protein that has an important regulation related to certain disease. Is it a protein is located here in class in the group of protein here or here? So actually we can analyze this protein interaction using clustering technique. So how to find protein target? The detailed question is, what are the criteria that can we use to identify the most important protein, that have a important role in the, for example, in the mechanism or metabolism or regulations related to certain disease. What characteristic can distinguish one node or one protein from another? So this is the common question. Okay. Yes. If you want to, for example, choose the best student in your groups or your students, so you just give them quiz, for example, or examination that measure the competency or the competency of your students. This is like this. But in this case, we use the topology matrix to distinguish one protein from another protein. So we use centrality measure, which node is the most central or important. So this is the most common question: which node is the most central or important in network? Like for example, in media social, so maybe the popular singer have become a central in the community, like this. Okay, or the celebrities, for example. But in this case, we would like to know what the most popular, what most critical or important node or protein in the protein-protein interactions. So the measure is first is local measurement degree and the relative measurement of all nodes in the network. For example, closeness between and eigenvector. Degree is, I already mentioned, explained that the intuition is more connection, more important. Is makes sense, yeah. And closeness, calculating the average distance or shortest path from node E to node I to all nodes in the network. So the intuition is the closer the nodes are to all nodes, the more important they are. Okay, because they are many friends. They have many friends. Yes, many close people. So it's more important. Pitwiness, the pitwiness is intuition is the more the number of shortest path that pass through the node, the more important the node is in the network. So if you, for example, pick up a node that can bridge, can connect between two groups, so you are important. You are important for these two groups. Okay. Then eigenvector is the more important nodes are adjacent to the node, the more important the node is. So our neighbor is very important for us because they are close to us. So if you have a trouble, then they will be the first person that will help you. Okay, and this is the analogy. Okay, so we try to make a transformation of PPI to centrality features. So from the complex network here, then we try to transform this network into the betweenness, closeness, degree, stress, and we got a value here. Don't worry, because they will cytoscape will do for you. Okay, cytoscape will do for you to calculate this value. Then we also can use the clustering PPI, because clustering can suggest possible function for members of the cluster which were previously uncharacterized. And in biological net, a cluster is a group of related genes. So especially the genes that have a similar function, they will group together. Okay, this makes sense, I think. We will use the cluster one. This is also already, we can add the plugin of cluster one in Cytoscape. This is part of the final project that will give to you. But maybe I just want to explain briefly that usually this clustering is based on the cohesiveness. So for example, first we assume that this, for example, there is an initial cluster that consists of C and E, B and D. And then we try to extend the cluster. For example, by calculating the cohesiveness value. Sorry, still in Indonesia, nilai cohesive, but actually this is cohesiveness value. So if you add, for example, A, first cohesive value is 0.625. Yes, because we have the 5 inner links here, 1, 2, 3, 4, 5. Yes, because the formula is this: number of each inner side of cluster divided by number of each inner side of cluster plus a number of its outer side of cluster plus penalty. But in this case, we assume the penalty is 0. So the first initial cluster, we assume that C, E, and B, D have in the same cluster. So we can calculate the cohesiveness value is 0.6. And then we extend to A. From this, we can have a inner cluster 1, 2, 3, 4, 5, 6. Yes, 1, 2, 3, 4, 5, 5, 6. So the inner cluster is 6, and the outer cluster is 1, 2, 3. So 6 divided 6 plus 3 is 0.997. And we try to extend to F. There is a 1, 2, 3, 4, 5, 6, 7, and 1 and 2 outer. So 7 divide 7 plus 2 become 0.778. So then we chose the bigger value. In this case, after we elaborate, explore the other node, then we have a final cluster here, C, B, E, T, and F. So this is the cluster one techniques. you will not implement it here using specific language programming, but just use cytoscape, and you just have a result, get a result resulted by cytoscape application. So, for example, from this complex network here, then we try to have the result, the clustering result here, and you can choose the p-value here. So the good cluster or the best clusters is with the minimum p-value. Okay, and also after we, for example, have a cluster, then we can rank the protein inside the cluster. You can rank by using, for example, degree, or by only between the centrality, or by eigenvector, eigenvalue, and so on. Or you can accumulate or consider all of parameters like a degree between the centrality and so on into one value. We call it as overall centrality. Overall centrality. So, for example, it is between the centrality. This is closeness centrality. This is, for example, other attribute. Then you should find the weight here. Yes, or coefficient. This coefficient actually calculated by using PCA to get the eigenvector and to get this weight. After that, you can implement this weight. So you have a formula of overall centrality, and you can calculate each node of protein to get their overall centrality, and then we can ranking or sorting the protein according to their overall centrality score, and then we can, for example, take the top 10 protein that have a highest overall centrality score. Yeah, for example, like this is the formula of overall centrality, and then we can examine or analysis the protein that have highest overall centrality to be a candidate of protein that have important role in the mechanism related to specific disease. Okay, thank you. This is, I think we still have 15 minutes for question and answer. Okay, thank you, Mr. Ahmad. Yes.
Yeah, thank you very much, Dr. Suman. We have had an interesting discussion so far, most especially on PPI. We know that nowadays developmental biology, or like synthetic biology, is one of the fields that is emerging in all aspects in all fields of research, most especially in drug design. So I want to remind our participants that there are two ways you can ask your questions. You can ask your questions by raising your hand. We'll recognize you, and you can ask verbally, or you can leave your question in the chat room. So far, we have had an interesting presentation from our two presenters this morning, and it's about time now you put in your question, your very interesting questions that you want to look forward to in the future, probably in research, or maybe just to mentor other people, because we know we have a diverse group of people here. We have docents, lecturers, we have students. So I think it's about now you just put in your questions to Dr. Kusuma for responses, for accurate responses to some things you didn't understand during the lecture, or somewhere where you have some difficulties. So the time is now. So while we are waiting our participants for questions. Probably some of them are taking time to type. I would like to ask a few questions to preliminary questions so far to Dr. Kusuma about PPI. So far, Dr. Kusuma, what is the novelty? What is new about PPI in traditional medicine? What are the relationships? What are the correlations? What are the basic correlations between PPI and that is traditional medicine or JAMO currently, like as of 2021?
Okay. Yes. Can you hear me? Yes.
Yes. Yes.
Actually, thank you, Mr. Ahmed, for excellent questions here. This is actually our homework. Firstly, in the first speak, for example, first speaker from the Dr. Danang that highlight the importance of scientification of JAMU. Actually, why maybe the questions is why JAMU cannot grow highly or grow like traditional medicine. Yes, because we cannot, if for example doctor or medical expert, medicinal experts ask us about the what actually the mechanism of JAMU can cure, for example, specific disease. Can you explain? Because usually researchers in traditional medicine start from the product or the plant that maybe already passed on generation to generations. So the experiment is actually for example just to prove, for example, using the in vitro and in vivo and in vitro and in vivo experiments. And when the question is extend to what about the effect of the, for example, multi-components effects, so maybe we cannot explain by using in vivo experiments. So actually by using network pharmacology, we try to give the alternative solution if this approach is agreed or maybe can be understood by society. We can, by using a computational approach, we can show you the interactions between compound containing in plants with the protein targets that represent protein target that represented the specific disease. But the problem is not many people accept this approach. For example, if using machine learning or artificial intelligence, because many methods in artificial intelligence is black box. You know, like for example, we develop the software that can, for example, predict the condition of a COVID patient, for example, like that, by using artificial intelligence. But doctors still not confident to use the decision, because
oh yeah, yes. Okay, yes, okay.
Yes, because sorry, still because the communication. I think that there is need to create the communication between interdiscipline, so that the computational approach that can describe the interaction between compound in herbal and protein target can be accepted by other scientists or either researchers in other discipline. Okay, maybe this is my answer.
Okay, thank you very much. So far, we have not had any question yet or any sign of someone wanting to ask. So we know that recently there has been a breakthrough in bioinformatics, maybe system biology, with this Google software developed, although it was developed previous years back, because 2007 was the first time, 2018, but in this year, 2021, which is AlphaFold. AlphaFold is this Google artificial intelligence program they use to model proteins. Yeah. So okay. You know, like recent advancement shows that, because recently I was listening to it and they said they are able to predict about 500 proteins within less than 1 minute, and their target is to have proteins, about 1,000 proteins modeled within seconds. So, and this with that protein-protein interaction and network analysis, what is your take? What is your advice to students going through, or what do you think about AlphaFold so far with the future of bioinformatics and system biology?
Okay, thank you, Mr. Ahmed. Yes, actually, this talking about the AlphaFold actually is related to the maybe the the session of Dr. Setianto Triwayudi. But in this session, I just want to give you the other perspective. Actually, AlphaFold is need high performance computing, you know. Working with the simulation, molecular simulation is computational time. Yes, it's high computational time. Need high computational time. So, for instance, because AlphaFold is actually introduced by Google, and they have infrastructure, high infrastructure, so they can do that. But maybe in Indonesia, we can, I don't know, it's very difficult, for example, to develop applications like that. But we try to introduce the simpler method. But I don't know, we still don't evaluate the accuracy. In AlphaFold, we should have for example, 3D dimension data or something. But in our case, we only need 2-dimension, I mean 2-dimension data, like text. We need only text data, for example, this protein name, and then we try to convert to the numeric data, like the fingerprint features, and also for protein, we only for example, extract the features from, for example, the sequence as amino acid sequence. So the process is not so time consuming. So we do not need the, for example, high performance computing infrastructure. We can run this for example, this application in the simple way, like this. So and also we do not need to find the, for example, the I don't know the AlphaFold there, but maybe we should find the 3D data and so on. But in this case, we introduce the more simple thing. Okay. Maybe, but maybe tomorrow you can ask Dr. Setianto Triwayudi that. Maybe
okay. Since we have a session on that, I believe it will be also another interesting session for tomorrow for our students. So probably since up to now we don't have any questions, and maybe we are approaching our break time, I would like to ask you few questions. Probably it might be our closing questions. We know that many of the participants here some of them are lecturers and some of them are students and potential researchers. From your experience in protein and protein interactions and network analysis, I would like to know what are some of the challenges you have experienced working with protein-protein interaction and network analysis, and what did you do to overcome these challenges? And then what are some of the advices you have for students or lecturers or researchers who are interested in going into this field of research? Thank you.
Many questions.
Yeah. So
Okay.
it's challenges. How did you, some of the difficulties you experienced, how did you overcome these difficulties, and what advice or motivation you have for people going in this direction?
Okay. The challenges actually by using protein-protein interactions network analysis is to find the biomarker, because now in the world we already move from the traditional, not traditional, conventional medicine to precision or personalized medicine. So the core of personalized or precision medicine is to find the biomarker that represent the profile, the genetic profile, or also the phenotype profile of a person. So, for example, we can before this era, people find that drug and then assume that this drug can work to all of person in the world without knowing the profile of genetics or something. So finding the biomarker for precision medicine is very challenging, and I believe that protein-protein interaction network analysis can be used to solve this problem. This is the first. But the difficulties is because I talk in Indonesia. I don't talk in in Japan or in Europe that already modern and something. In Indonesia, the communication between computer scientists and, for example, medicinal scientists, pharmacologists, or chemists, or biochemists, or biologists is not so good, still not so good. So computer science research by themselves, chemists research by themselves. There is no collaboration, the strong collaboration. So if, for example, I find the specific protein target related to specific disease, I cannot understand what actually the mechanism or the importance of this protein. And I didn't find the partner that can explain to me. I already socialized this approach through workshop, through seminar, international seminar, but still there is no response. The good response, so that we sit together, we discuss it together, multidiscipline researchers to focus on is it possible to we implement this paradigm to move from the traditional conventional paradigm into the modern paradigm, especially related to precision medicine for herbal medicine or jamu. This is the difficulty. So what should we do? Yes, we should create the communities that work together in the same problem. And also the second problem is infrastructure. High performance computing infrastructure. So we hope IPB University in this year will develop HPC, so the problem will be can be solved. Okay, maybe is it answer your question?
Yes. I think you covered most of it. We have, although we are running out of time, but we have one question here. I think since it's our only question so far from the crowd, we'll have to prioritize it because we are going for break. So we urge you guys to please bear with us. So this question is from MF Romdendin from EPB University. It starts with an appreciation. Okay, I would like to ask Dr. Wisnu, is there any strategy that can ensure the society, especially government, that this modern method of drug design can provide best method for drug design and can sometimes in the future, replace the conventional method to make or design drugs? I think probably this question is trying to say that how can we convince the general public and the government, that this new technology that we are bringing, how that they can trust it, and that sometimes in the future it will be able to replace the conventional method of drug design for traditional medicine. So I think he can. That's the question from my understanding.
Okay, thank you, Mr. Fahruri. The first, the answer actually is communication still. Actually, the government already have a regulation to about the scientific of jamu, but the action or implementation maybe should be discussed with not only with government, academia, but also practitioner like industry, herbal medicine industry, and so on. And we should enforce for example, the scientific activities like this. For example, summer course, workshops, or seminar, international seminars, or also discussion in limited discussion, but focus to discuss what actually the possibility to bring the modern approach in drug discovery, especially for herbal medicine, so that we cannot, so that we can also follow the condition or the we can follow the research, the future,
progress.
The progress of research in the world, because in the world now, many researchers focus on the precision medicine, so we can also follow the directions. So we cannot our position is the same with them, especially in the modern country like Europe, America, Japan, and so on. Maybe like this. My questions. My answer. Sorry.
Yes. Okay. The person said thank you. We have one more question. I don't know if our MC will allow us to go through that question, but it is an interesting one. So meanwhile, please bear with us. Maybe we'll also talk to Dr. Gusma to speed up the answers. This question was sent directly to me. I don't know, probably it's a mistake. The question is from Eko Praja Hamid Wijaya from EPB University. The question reads, technology in PPI prediction as described previously may not be accepted by all academic circles. And this is a vital gap because we are now in the industrial era 4.0. In your opinion, what are the steps to close the gap? That is to make sure that every academic sector accept this prediction, this opinion, or this technology of PPI, with the hope that the process drug discovery can be carried out effectively and efficiently, where collaboration between human and machine computers in circle is, in parentheses, is needed. So how can we close this gap to make sure that people accept PPI, like protein-protein interaction network analysis, in our research centers? Because we know that some people accept it, most especially computer science people, but non-computer science people don't accept this this way of drug design. So how can we make sure that everyone accepts it as one form of research in order to advance research in this industry 4.0? Thank you.
Okay. Yes, maybe this question is similar to the previous, but I just want to emphasize from the perspective of computer scientists, our responsibility as computer scientists is to transform the PPI, or the concept, for example, PPI or something, become the simple language, not simple explanation. So this is our challenge, how to make a simple explanation about PPI so that the general public, yes, can be understand the concept. This is actually because many participants here do not answer make a question. So I feel that I'm still fail to explain the protein-protein interaction in a simple way, because not so many questions from the participant. This is our challenge. So from this perspective of computer scientists, this is our challenge, how to make a simple explanation so that the PPI can be understand easily. But from the perspective of non-computer scientists, they should be proactive to learn about artificial intelligence in the generic explanation. For you can for example just read the books from of artificial intelligence, but not the conceptual books, yeah, but generic books. Many books about the artificial intelligence written by popular scientists in computer science. So by read this book, then we hope we can have a open-minded, yes, open perspective and mind to accept the new technology. Maybe this is my question.
Yeah, okay. So
my answer.
Yeah, okay. My takeaway from the question and answer is that we can force people to accept, but we can make it so simple that people will understand, and we can make it simple, and we prove that the validity of these methods through through scientific results. That yes, indeed, these methods they work effectively, they work efficiently, but you cannot force the public to accept that, to accept or to adapt to these methods. But it is the challenge of people like Dr. Kusuma to make sure that yes, indeed, the general public understand these methods in a simple way, and then so that they can be interested in these methods to conduct further research, to collaborate, and to advance research in this industry. So I think this is what I understood from Dr. Kusuma's response to your question. And so thank you very much, everyone. We want to thank Dr. Wisnu Ananta Kusuma for his brilliant presentation. I believe that this topic is new to almost all of us. This PPI network analysis is new to all of us. Probably that's why many questions didn't come, because we don't have the basic background or baseline information on this. So I believe from here on, many of the students have been exposed to this topic. I believe many of them will now go and venture more into information as relates to this topic. So we'll get back to our MC Shadila for closure, for break. Thank you very much, Dr. Kusuma.